Welcome to Sanjoy's Geometrifying Trigonometry. Today we are trying to tell you how Gtsimplex objects look like. These kind of things are Gtsimplex objects. Whatever it is looking good, but sometimes it looks odd and like the triangulated objects. And we will find that several times you will see these kind of objects in your lifetime, in the triangulated cases, or in Delaunay triangulations, or in graph theory. You will find this kind of objects several times where different triangles are glued together. It looks like the glued triangles because there are common edges, and whenever you will see these kind of objects, surely it is a geometrifying trigonometry Gtsimplex. Gtsimplexes are looking like this kind of objects where different kind of triangles are glued. Okay, now we know that in any height and distance problems in our school days, or in surveying problems, in the land surveying problems, or in linkage mechanisms for mechanical engineering, where dynamic things are there, where the linkages are also the glued triangle formations, like the trusses of bridges. If you check the Eiffel Tower or Howrah bridges, the Rabindra Setu, and any kind of bridges where there are several steel members are connected, or any kind of members are connected, which looks like the glued forms of triangles. And all these glued forms of triangles have a property like this kind of arrangements where every line segment has its special meaning. The angles formed in the triangles are also having some special meaning. I have taken this example from the first basic chapters of trigonometry books that you find in your textbooks, and we have seen that if we try to find these kind of expressions, suppose we are trying to find these kind of expressions from this kind of geometry, then you can easily do it. And all these things are from school days. We are doing these kind of things almost every day, and engineers also use these kind of techniques. First they draw these kind of pictures, then they generate these kind of equations or these kind of expressions in trigonometry. But before geometrifying trigonometry, before Sanjoy's geometrifying trigonometry, no one was trying to prepare a canonically axiomatically formalized model to represent these kind of expressions into these kind of pictures. Note it, these kind of expressions you can see in trigonometry. These are algebraic expressions which has deep geometry meaning. How are these geometry meanings? These geometric meanings are like, the most basic form is the left side is representing some line segment, and you can see it here, one line segment is here, and this is also representing one line segment, sin alpha cos beta here, which is also visible here, the sin alpha cos beta. This is a line segment, and cos alpha sin beta is another line segment, you can see here, and they are naturally summable because they are collinear. And we can think of another line segment which is like this, which is not drawn here, but it could occur. We could draw another line segment like this, but this is also not shown here because it was not necessary for these cases. We could imagine that one such line segment could come here and two triangles could get glued. That is also not shown here. We could prepare another line segment here which could show the gluing of two triangles. That is also not shown here. We could draw another line segment to make a glued form of two different triangles, but that is also not shown here. There are reasons why these kind of things are not shown here, and why these kind of line segments are not necessary, and that kind of questions are already answered in these kind of expressions. But those exploration and those inquiries regarding these trigonometry forms were never examined before Sanjana's Geometrifying Trigonometry, and this is an entirely new subject where we have made a canonical formalization for constructing this kind of expression into this kind of Gtsimplex. Gtsimplex means the Geometrifying Trigonometry simplexes. It is like simplex, so we call it Gtsimplex. And there another concept called locked set, that is also important subject, and we will discuss about locked set also. Locked sets, what are these locked set? When these kind of Gtsimplexes are added, like here we have seen one addition is done, and this addition subtraction for the different Gtsimplexes prepares a locked set. And when we will discuss with the power series situations, there we will see the locked set concepts. In Geometrifying Trigonometry, we discuss about all kind of symmetries. We know from the Kleen's 4 groups and from other kind of 4 groups, that is SU4, SO4, and there are different kind of symmetries. And so in Geometrifying Trigonometry, plus is also of 4 types, because geometrically they have 4 different meanings or 4 different symmetries. Multiplication are also of 4 types, and though they also have different meanings. Geometrifying trigonometry is a non-commutative thing, where sin alpha into cos beta is not geometrically same as cos beta into sin alpha. I repeat, sin alpha into cos beta has a different meaning than cos beta into sin alpha. Although they have the same numerical value, that is the final line segment have the same length, but algebraically that can have the same length, but geometrically they have entirely different pictures and entirely different Gtsimplexes will form. From this expression, suppose we have this kind of expression, and on the left side there is only one expression, so we can think about that there are 4 different line segments are possible. But here, there on the right hand side there are 2 different Gtsimplexes, because the multiplicative forms of the power series or any kind of expressions, the terms where only multiplications are involved, those make the Gtsimplexes, which are the triangulated pictures like these. And when they are added, when the plus is used, then it prepares a locked set. I should explain it, and I should tell it here that this whole thing makes a locked set. And locked set is a concept made by Geometrifying Trigonometry. In the Sanjana's Geometrifying Trigonometry, we will see the concepts of Gtsimplex and locked set. Plus, minus, into, divide, all are applicable for Gtsimplex in some different way, and plus, minus, into, divide are applicable to locked sets in some different way. The locked set has 2 different kind of concepts, basic concepts of plus and minus, and the plus and minus are of 2 types, that is the natural additions, the natural summability, and forced summability. Natural and forced. Natural and forced. Natural summability are of 4 types due to the force symmetry, and forced summability has interesting topics of the 2 different kinds, that is cumulated summations and forcefully aligned summations. That is the cumulated summations and forcefully aligned line segments are done. Suppose if these 2 line segments were not collinear naturally, then we could rotate the Gtsimplex and we could make these 2 collinear, and the whole behavior of the geometry could change, and we could get more deeper insights for those kind of things. So we have a vast ocean of inquiries on these kind of things, and even in some cases you will feel that all these are the vertices and these are all edges, so it can turn into a moving salesperson problem, it can turn into a graph theory problem, it can turn into a triangulation problem for the finite element analysis of the force distributions. It can turn into a problem for the linkage mechanisms, and if alpha and beta are changing continuously, then we can see dynamic geometry, and like in GeoGebra or in the Pro Engineer softwares or in SolidWorks, we can see this kind of animations while we design the bridges, trusses, and then we can see that this kind of pictures we always see, and we can adjust and readjust these values of these angles. These angles are the seed angles. Suppose in these cases we have seen that only alpha and beta are there, and alpha is what are kind of angle which is same or different than beta. So two different kind of angles, two different kind of seed angles are involved in this case. So here we can find two different kind of similar triangles are involved in this whole process of gluing, and it can have the different kind of subject matters to discuss, different kind of inquiries, the number of similar triangles involving in the whole locked set. That is another question of the analytical series, where we can represent the expressions as a power series, but every power series can have a Gtsimplex. Since the numbers are the ratios in our previous videos, we have already shown that numbers are approximated. Even the irrational numbers taken up to the 15 decimal places or 6 decimal places, we can think of it as a rational number practically, and if we take it as 6 decimal places, then we can multiply it with the 10 to the power 6 on the numerator and denominator, and denominator can have a 10 to the power 6 and numerator can have that irrational number multiplied with the 10 to the power 6 and rounded to the 10 to the power 6, and that is sufficient, quite sufficient for mechanical engineering problems until we are trying to go for the spacecraft missions, and up to 15 decimal places is sufficient. So for several cases in engineering solutions, and for last 22 years I am working for engineering softwares, and in CAD also the 6 decimal place suffice for the civil engineering problems or mechanical engineering problems. No one is going to bother more than that precision. So every rational numbers is also considered as the rational numbers up to 6 decimal places, max up to 11 decimal places. Okay, that is also a rational number as for the engineers. And our fundamental motive is to prepare the geometric meaningful things out of any algebraic expression. I am telling here for the trigonometry expression, but it can occur for normal real number polynomials also, where we can think that every term which are plus minus done, every term, multiplicative terms are considered as the Gtsimplexes, and all these Gtsimplexes can have these kind of pictures. Sometimes it looks odd, but Gtsimplexes have this kind of pictures. Now, in the Gtsimplexes, multiple triangles are involved, and with every triangle there comes the 3 line segments. Obviously, naturally, we will see 3 line segments and 3 points. But when the total Gtsimplex is formed, we will see that total number of points is not equal to 3 times total number of triangles, because some of the points are overlapped on one another, some of the lines are overlapped on one another. So number of edges in the graph theory graph has the different calculations in the Gtsimplexes. There are the several theorems in the Gtsimplexes with which we can decide the graph theory geometries and graph representations. Actually, we should say it in that way. And the beautiful thing in the Gtsimplexes is that they are all represented as the trigonometry ratios. So we can assume that the triangles are right angle triangles, and where different values of alpha, beta, theta will be there, and for that reason the triangles can look different. But it is also a point of inquiry in Gtsimplexes that how many similar triangles you can see out of these things. With the analytical calculations, mathematical calculations, we can decide many kind of network problems or the moving salesperson problems out of these kind of things, if we can put it in the right way. Now, one thing more we have to discuss, that here in the Wikipedia diagram we can see one line segment is decided as a 1. In geometrifying trigonometry, in Sanjoy's geometrifying trigonometry, it is taken as a L, capital L, which is any line segment which we consider as the first given line segment. The whole journey of constructing the Gtsimplex, that is every term of the power series, is started with the single common line segment. The line segment taken for the first Gtsimplex is the same. It is the convention that we will take the same line segment for the second term, we will take the same line segment for the third term. In that way, in every term we will take the same line segment and we will start the construction, and for every different term we will get different Gtsimplexes where the first line segment, the first given line segment, is common for every of these terms. And so we can assume that all other triangles are distributed around and in the neighborhood of these initial line segment. So we can get assured that the line segments will not jump here and there out of the locking behaviors, of logically reasonably locking behaviors of these trigonometry expressions or in any algebraic expressions. Suppose in any algebraic expressions x is any value, x is any number and any real number, then we can consider x as tan theta, because tan theta can take range from minus infinity to plus infinity. We can take it as a tan theta. We can take it as a sec theta, cosec theta, cos theta, sin theta. Anything depends upon 0 to 1 or minus 1 to plus 1. The value of x can be between minus 1 to plus 1, or it can take the values between 0 to infinity. It can take values from 1 to infinity. It can take many different kind of values, and we can choose different ratios, trigonometry ratios. There are the different theorems in geometrifying trigonometry to decide these kind of ratios, which ratios fit best for the geometric series. Some ratios work better for hyperbolic series, some ratios work better for Ramanujan's polynomials or the equations. Some of these ratios work better for Cauchy series and abelian series. So the natural summability is a point of concern in geometrifying trigonometry also. Now we are going deeper into the geometrical discussion here. The left side of any trigonometry expression represents some line segment. Suppose it's the simple thing, and if it is a ratio, then we can consider it as a triangle, and if this is a ratio, right side is also a ratio, then we can consider it as another triangle. And we are trying to prove that they are two ratios which are equal. That means the both sides of these trigonometry expressions in that case will represent as two similar triangles. The similarity is proven through the equality symbols between the cases where there are the ratios. Here it is not ratio, because here the denominator is 1, and for this side also the denominator is 1. That is, the initial line segment is the input line segment. And the division in geometrifying trigonometry is described and canonically formalized and defined as the input line segment is the denominator and output line segment is the numerator. So there's a different video in the previously I have already uploaded, where I have already shown the nature of the gluing due to the multiplication, nature of the doublet, the properties of the doublets due to the divisions, and how we should consider the multiplication of ratios, how we should consider the construction of the triangles from given two line segments, one at the numerator and one at the denominator. The denominator part is the length of the given line segment. Either it is complicated thing, but it can happen that the denominator is the Gtsimplex, where the output line segment is the input for the whole process, and for the numerator can also become a Gtsimplex or log set, where there is an output line segment which is the output for the whole system. I will describe it in the separate video, that conditions. Log set will also have a common line segment, as I have already told here, that every terms in a log set are started from the initial line segment which is common for everything. Now if this line segment is common for every of these terms, then after the locking of all these Gtsimplexes, logically locking due to the plus or minus signs in between, it will form a log set. And this log set means large number of points, large number of line segments, and large number of triangles will get related due to the geometric construction rules. And when alpha and beta or theta, all of these things are changing, all the line segments will take their different positions, but the rules of construction will remain fixed. I will suggest you to use GeoGebra, that is a free software for educations and for students, so that they can understand the flavor of dynamic geometry. Actually, this subject is called the dynamic geometry, where you can change the parameters and you can see the visualizations of the whole things if you change these values of angles. So until you are practiced with GeoGebra, you cannot actually understand the flavor of dynamic geometry. I don't expect that you people are engineers, and I don't expect that you people have used the smart softwares like Pro Engineers, CATIA, SolidWorks, or Tekla, or these kind of softwares. I don't expect that you people know these parametric modeling systems. You don't know. You can easily use GeoGebra or geometry expression kind of softwares, where those are for education purpose, and with those softwares you can play with the dynamic geometry. I have several GeoGebra files for geometrifying trigonometry, and I am adding also for these files. There are 65,000 number of problems in our 9th, 10th, 11th, 12th and joint IIT exams, and I have the mission to make all these trigonometry problems, at least the trigonometry problems, in geometrical way. I will try to explain all of these problems in geometrical way, such that you can have the bigger insights on these geometric representation of these whole things. Now I will go deeper into this particular solution. We can do the same thing for everything, but first natural question comes here is, if we take this equation, suppose the left side has the 4 line segments, specifically 4 line segments on the 2D plane, because there is only one ratio involved here. On the right side, the 2 multiplicative terms are there, so every Gtsimplex are getting added in 4 different ways, because the plus is 4 types, the summation type 1, summation type 2, summation type 3, summation type 4. These are the 4 symmetric constructions. For every addition, we have the 2 terms on the both sides in the abstract syntax tree, and it is a quad tree. Actually it is forming a quad tree because the 4 branches are opening up. From the plus, there are plus 1, there are 2 arguments, and these are non-commutative because sin alpha into cos beta is not same as cos beta into sin alpha, and the same thing is occurring here. And multiplication has also 4 types of symmetries that I have already demonstrated in 1 or 2 videos in the previous, in this same channel, with the detailed demonstration of why the 4 kind of orientations and 4 kind of gluing are occurring here, that 4 symmetries are working. So for every multiplication we have 4 options opening up: 4, 4, 8, 4, 12, 4, 16, 4, 20, 4, 24, plus 4, 28, plus 4, 32. Now 32 pictures of Gtsimplex will involve, and since they are non-commutative, we can see there are 2 times more, so 64 different arrangements are possible for this simple expression. And out of these 64 arrangements, some of these will look exactly like this, some of these will look different from this, but the story, the reasoning will remain same. You will find these kind of cases where cos alpha sin beta is not collinear with sin alpha cos beta in some of these arrangements, but some other way we will get some different insights. Now here we can see the initial line segment is given here. From that, when we take cos beta, one line segment is constructed, then cos beta is taken as the input line segment. For the previous, suppose we should do the numbering of these triangles. Suppose this is the triangle 1, this one is the triangle 2, this one is the triangle 3, this one is the triangle 4, this one is the triangle 4, and in that way we can see that some of the line segments are overlapping. Suppose this line segment is overlapping line segment, so we can consider the 2 different edges are overlapped here. Similarly for this line segment also, for the cos beta line segment also, 2 different line segments are overlapped, one due to the triangle 1 and another line segment from triangle 2 are overlapped. The output of the first line segment is taken as the input of the second triangle. The output of the first triangle is cos beta, which is the hypotenuse of the second triangle. So cos alpha into cos beta is the final output, and final output or if we take that sin alpha cos beta is the final output, this is the wrong to say in the geometrifying trigonometry, because we are getting cos beta first, then we are taking sin alpha. So we should consider this line segment as cos beta sin alpha instead of sin alpha cos beta. So it's, as per geometrifying trigonometry, it is a bad habit to write it in this way. It is bad habit because the first thing first, when cos beta is done first, I should write the cos beta first. Then sin alpha is done later, so I should write sin alpha later, not as in any commutative algebra. It is not like this. That in the similar way, when this one is the L, this in the first triangle, the hypotenuse is the initial line segment, and then it is the input line segment, and from that we get the output as the sin beta. So we should write sin beta first, and sin beta is now turning into the hypotenuse of triangle 3. So they are gluing together, and the gluing is multiplication. Actually, the gluing is multiplication in geometrifying trigonometry. This kind of gluing means it can become the input for the second line segment. Now sin beta is the input, and sin beta cos alpha is the output. Final outputs are always the nascent line segments, that is, no overlapping is there. All of these final line segments, like this one is output line segment, this one is the 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 output line segment, and this one are the output line segments. And output line segments are of two types. One is the genuine output line segment, and another is the complement line segments. Whenever we construct any triangle from a given line segment, we have to generate two line segments. One is taken as the output, and another is taken as the complement line segments. And sometimes the complement is taken as the output, and then the other line segment turns into the complement in that case. And it depends upon the requirement of the final addition. Suppose this is the Gtsimplex, sin alpha cos beta is added with cos alpha sin beta. So sin alpha cos beta is the output line segment for the first Gtsimplex, and cos alpha sin beta is the output line segment for the second Gtsimplex. So this one is the Gtsimplex 1, GTS1, and this one is the GTS2. So I should write it here. I should write it here like that. This one is the Gtsimplex 1, and this one is the Gtsimplex 2. Gtsimplex 1. And this one is the Gtsimplex 2. And when two Gtsimplex have, every Gtsimplex will always have a output line segment and a complement line segment, and initial line segment is common for everything. Gtsimplex 2. So this whole thing is a locked set, and every of these Gtsimplex are having the common L. Here also it has the input as a common L. L is the input line segment for this also. For this also it is the input line segment, and the L is input line segment for this also. And these are the output line segments. Every Gtsimplex has the output line segments, and the output line segments are added. Actually, output line segments, every Gtsimplex have one output line segment, and these output line segments are added in 4 ways to check which of these best fit as natural summability. Best fit for natural summability means, obviously, best fit for natural summability means they are best collinear. Ultimate output is collinear, and if that is collinear, then it can form a good triangle. Suppose this one is a good line segment as output, and we can consider it as another triangle, and in that case one output line segment is there, and we can take a triangle with that. And this is also constructible from some other conventions, and in that way we can think the natural summability is a case in the Gtsimplex. In that way we can do the plus minus into divide with Gtsimplex. The plus minus into divide, the plus is demonstrated already here. That plus means the final output line segments are aligned in a single line, either naturally or forcefully. The forcefully alignment are also of the cumulating type. I should tell a little about the cumulative addition. Suppose two output line segments are in this way, and then we will consider this total as a summation. And for forced alignments means if one output is like this and another output is rotated, we will rotate the whole second Gtsimplex such that we can get the outputs collinear, and then forcefully aligned, then we get the whole locked set in a different way, and the rule is tightened. In that way we will get another kind of geometry and different kind of inquiries will come out. Reversing the direction of the output line segment does the negative things like the vectors, but you have understood that line segments are not vectors, because for the vector cases the arrowhead is either on this side, arrowhead is either on this side, because the symmetry, if a locked set has another line segment on this side, if we take it the different summation, then it will get in reverse due to the mirroring. We can take the same vector as a reverse parallel thing like this, and we can have this invert there. In the same way we can think the fourth orientation also for the same line segment. So we can have the four different kind of, we can think of the four different kind of sum, four different kind of subtraction. So things will generate large number of images, but we will get large number of insights also, because it will turn into the problem of geometry, it will turn into the problem of network flow, it will turn into a problem of moving salesperson problem, trigonometry expression can turn into a problem of triangulation, it can turn into a problem of linkage mechanism of mechanical engineering, it can turn into a problem of the bridge design, it can turn into a problem of land surveying. So a vast number of options open up when we try to represent every trigonometry expression as a geometric object. That is a big pervasive domain on which we can work, and we can generate more theorems, and with that we can hit the electronic industries, since the Fourier expressions can give us one kind of solutions, but geometrifying trigonometry can give us more deeper insights, and with that we can get more kind of data analytics. And in data science domains also we will find several geometric insights from the trigonometry expressions, and so that we can analyze data more, we can model several statistical problems with this, and in that way it can explain more things than complex numbers also, because complex numbers has only one and two kind of symmetries, but in geometrifying trigonometry we take care of all four symmetries together, and we construct the triangulated images out of given trigonometry expressions, out of any given trigonometry expressions. Only two limitations are currently found here are the fractional powers are not taken care in geometrifying trigonometry, and another thing is that when suppose inside any trigonometry ratio, when any big expression like with exponential series expression or any other big Gtsimplex like expressions are written inside sine bracket or inside the cos bracket or inside the tan bracket, in those cases we take it as a pure number, we don't consider it as a Gtsimplexes, because in geometrifying trigonometry we have not yet found any canonical formalism for those cases where within the bracket of the trigonometry ratio, if we are trying to write a big expression, big algebraic expression, then it is meaningless in geometrifying trigonometry. Up to now we can find some meaning, we can find some geometric meaning some days later on, but currently it is not available in the definition of geometrifying trigonometry. Thank you. With New videos we will come with the locked set algebras also, plus minus into divided with Gtsimplex also, and we will try to explain the geometric meaning of every trigonometry problems, every trigonometry expressions from the school days to college days to professional world, and in that way we will get bigger insights on the geometric way of thinking and the ways of the geometric reasoning on the trigonometry expressions. Thank you.